Welcome to the next video. So this is another video in which I will be solving previous year KTU problems. Okay. So this question is for civil engineering S3 MOS. So this was asked in 2018 April. It was asked for 8 marks. So it's a very simple problem, direct problem. So module 5 of MOS, there are three portions: stress transformation, then we have torsion, then we have columns. So this is from the column portion. This can be very easily solved with simple equation. So I'll read the question first. Calculate the safe compressive load on a hollow cast iron column with one end rigidly fixed and other end hinged. Okay, of 15 centimeter external diameter, 10 centimeter internal diameter, and 10 meter in length. Use Euler's formula with factor of safety 5 and E equal to 95 kN/meter. So first I will draw the column here. The length of the column is given. The boundary condition I will clearly draw. So it is telling that one end is rigidly fixed. So this is how you show rigid connection. The other end is hinge. So this is how you show hinge. Okay, so this is rigid. This is hinge. Now the length of the column is given as 10 meters. 10 meters. Now, the moment you get the length of the column and the boundary conditions, you have to write the effective length. Effective length in this case is nothing but original length upon root 2. Okay, one end fixed, other end hinge. The effective length is L upon root 2. So this is nothing but 10 upon root 2, which comes out to be, so we'll just calculate that. Upon 5 root 2 or 7.07. Okay, so 7.071. 7.071 meters, or I can write 7071 millimeters. So this is the effective length of the column. Then the dimensions of the columns are given. So it's a hollow column. It is telling that 15 centimeters is the external diameter. So external diameter will give us 15 centimeters. Capital D I'll call as 15 centimeters. So I'll write in millimeters, 150 mm. And internal diameter is also given. Internal diameter is given as 10 centimeter. So small d is given as 100 mm. So be careful about the units. Then what is the other data given? Another data is given is E. E is 95 into 1000 Newton per mm square. So we know that Newton per mm square is nothing but MPa. Okay, so you have to remember that 1 MPa is 1 Newton per mm square. So this much is then they have to use Euler's formula. Euler's formula or Euler's formula, it is given by P equal to pi square E I upon LE square. So the student is expected to remember this formula. If you remember this formula, the problem can. There are two formulas in column section of this module. This is one Euler's formula, the other is the Rankine's formula. Yeah, then what all we know? We know pi is constant, E is given, I has to be calculated, LE is not. Okay, now we'll quickly calculate the value of I. How do you calculate I? I for a hollow circular section is pi by 64 times capital D raised to 4 and small d raised to 4. So this is nothing but pi upon 64 times what is capital D? 150 square minus what is small d? It is 100. Okay, so let's take out the calculator and calculate this. So we will put the values. Pi by 64 times 150 square minus 100 square. So this gives our value of I as 613.59. Okay, so sorry, 150 raised to 4. So I made a mistake here. I was also thinking why the value of I is very small. This is 4. So I'll clear in the 64. So 199,41750. So that is the value of I, 199,41750. Okay, so here I'll just clear the mistake. So it is to the power 4. So this is the value of I. The value of I should come always very large. So that is why when I was doing it, I used square, so I was getting smaller value. Okay. So I hope this is clear. This is how you find the value of I. Now you just have to plug into the equation and find the value of P. Okay, so let's just do this. So this is equal to pi square into value of E is given 95 times 1000 times I value is 19941,750. This divided by LE. LE is nothing but 7071 square. So we'll just calculate this very fast. So this answer is this is I will be stored in answer variable. So let's say it is pi square times 95 times 1000 times answer. So this answer is nothing but the value of I. Okay, 7071 square. So this gives me 373959 Newton. Okay, 373959. Or we can write it is 374 kilonewton approximately 374 kilonewton. Okay. Now one more step we have to do. They have given a factor of safety. So they are so this is the ultimate load. This is the maximum load it can take. But for improving the safety, we are reducing this value with a factor of safety. So safe load is P upon factor of safety. So this is nothing but 374 divided by 5. So this comes out to be 374. So this is 374 divided by 5. So nothing but 74.8 kilometer. 74.8 kilometer. Okay. Now factor of safety, it is to reduce the risk. Now if you are constructing this, actually it can take 74 kilonewton, but in practical purpose, because of a lot of uncertainties, this strength we may not get this much strength. For example, the value of E may not be this value. The value of the when manufacturing, the diameter may not be properly coming out, or maybe there is an initial initially the column we are assuming it to be straight. Initially there could be a bend in the column. All those things will reduce the load carrying capacity. So for a safety, we are reducing the capacity by some factor. The factor is 5 given here. So instead of 374, we are only allowing 74 kilonewton as the safe load. So we will tell when the column is used, don't put load more than 74 kilonewton on the column. Otherwise, it will fail. That is what we are going to inform the client or whoever is asking us to design. So I hope this is clear. So it's a very simple, straightforward formula which can give you easy 8 marks. That too very fast you can solve this. Okay. So we will again solve another problem in the next video. Thank you for listening.